As we continue talking about molecular orbital theory, and as we'll be talking about hydrogen and helium in just a second and their molecular orbitals, there's a couple of ideas I want to introduce first so we can sort of classify as we think about the orbitals. One is what we call a bonding orbital, and the other is what we call an anti-bonding orbital. So a bonding orbital is what it sounds like. This is an orbital that makes a bond. This is sort of what we think of as a chemical bond. What does this actually look like in practice? In terms of what the orbitals look like, it'll look like that first orbital I drew in the last video. It's an orbital that will concentrate, so this is representing, again, our probability. This is just like our other orbitals. This is a probability of where the electrons will be. Right? We can't say exactly where it is, but the highest probability exists right in between the two different nuclei. So this is our two hydrogen nuclei, so our two protons. And that is what will hold the molecule together. So bonding orbitals, electrons are located between the nuclei and hold the molecule together. These are lower energy, which is what makes the molecule stable. Anti-bonding orbitals are the opposite. So they will have some region in between the nuclei where there's a low probability. In fact, most anti-bonding orbitals will have a node right in between the two nuclei. And so we have a low probability right in the middle. Low or zero probability for the electrons in between our two nuclei where you would want them for a bond. And so these will tend to destabilize the bond. So if electrons are in these anti-bonding orbitals, it causes the molecule to want to split apart. So bonding orbitals, if electrons are there, will tend to hold the molecule together. Anti-bonding orbitals will tend to cause them to split apart. Hence the names, right? Anti-bonding, they're against bonding. So it destabilizes the molecule, and these are higher energy. So electrons will tend to, or will go into bonding orbitals first because they're lower energy, and then only after the bonding orbitals are filled, we'll start to fill the anti-bonding orbitals. We'll look at that in just a second. Okay, so let's start with our simplest case. And our atomic orbitals, we can think about combining to form these. So not just overlap, but actually combining. So let's look at hydrogen. We know that hydrogen forms this molecule H2. And you may have wondered, why does it not just stay as just regular H by itself? Helium does this, and then all the noble gases do. And we learned that hydrogen can make this molecule here, right, that forms a single bond. But let's look at this in terms of molecular orbital theory. So we'll have our two different hydrogen atoms. Draw them here and here. And each one will have one electron in a 1s orbital. So these red, and remember, this is actually a three-dimensional sphere, right? So this is not actually a circle, but a sphere. And in molecular orbital theory, what we do is these are mathematical functions, and we combine them as mathematical functions. We can add these, we can subtract these. Again, we're skipping that math, but that's what's happening behind the scenes here, is we are finding ways to solve the Schrodinger equation for a molecule, and using that to figure out the orbitals. And so when we do that, we can either add or subtract these. And with quantum mechanics, that's what you have to do, is you have one version where you add them and one version where you subtract them. So one thing with molecular orbital theory is that the number of molecular orbitals will equal the number of atomic orbitals that go in. So if we start with one atomic orbital on each atom, we should get, so that's total 2 atomic orbitals, we'll get out 2 molecular orbitals. And in this case, we'll get out one where they add together. I'll draw that in green. So again, I'll draw our nuclei here. And we get this shape like this, and we call this a sigma bonding orbital. Won't write bonding, we'll write sigma 1s to indicate that these started as 1s orbitals but now have been merged together. Now, why is it sigma? It's sigma for the same reason we talked about sigma bonds in the valence bond theory. It's because the electrons, the highest probability is right in between the two nuclei. So that's what we consider a sigma orbital, rather than being above and below. We're going to have pi bonds in molecular orbital theory, just like we do in valence bond theory. Now, when we subtract them, we will get an orbital that looks something like this. It's supposed to be symmetric here. And this is what we call, so our green one down here, this is a bonding orbital. And our red one on top where we subtract, this is our anti-bonding orbital. I'll try and move this away from behind my face here. There we go. And we call this one a sigma star. So we put an asterisk next to it. And it still came from 1s orbitals. So the anti-bonding orbital is higher in energy, tends to cause the molecule to split apart. We can represent this sort of pictorially. I'll use the figure from your textbook. Oh, I had it ready and now it moved. But we can represent the energy levels here. There we go, almost there. Graphically this way. That's what I'm looking for. Okay, so we can, these pictures on the side, these represent our atomic orbitals, and when they combine, this one on the bottom is our sigma 1s orbital, and this one on the top is our sigma star 1s orbital. And just like when we fill in electrons into atoms, we put the electrons in the lowest energies first, and the rules for filling the orbitals are just the same that you learned for atoms. You can only fit 2 electrons per orbital, and you'll always, if you have orbitals that are the same energy, like the p orbitals in atoms, you put 1 electron in each orbital first, and then you start pairing them up. So for hydrogen, we have 2 electrons, 1 from each hydrogen atom for H2, and they both go right here into this 1s, sigma 1s bonding orbital. So we can sort of view this as we put 2 electrons down here into this orbital, and no electrons in the anti-bonding orbital. Okay, so that's what's happening with our electrons here. They're being shared between the atom, and it's because we have formed this new orbital that represents that probability of electrons being right in between. Okay, so with this picture, what we call the bond order, we've been using this idea of single, double, triple bonds. In molecular orbital theory, we calculate this by taking half of the total number of electrons in bonding orbitals minus the total number of electrons in anti-bonding orbitals. I'll finish writing that out in both cases. All right, and so if we do that for hydrogen here, what we get is that it's 1/2 times 2 electrons in bonding orbitals minus 0 electrons in anti-bonding orbitals, which gives us a bond order of 1. Or just another way of saying we get a single bond, just like we predict with Lewis, with our Lewis dot structure with valence bond theory. We would predict the same thing, and that it's a sigma bond. So this is agreeing with the models that we have previously. What about helium? So helium, unlike hydrogen, does not exist as a diatomic molecule. It has the same orbitals to start with. So what about if we try to make helium-2? So we can draw the same diagram. We have our 1s electrons, and there are 2 of them for helium, for each atom. We're going to form 1 lower energy orbital, that's our sigma 1s, and 1 higher energy orbital, that's our sigma star 1s. And these look the same as the ones for hydrogen, so nothing really changes here. The energies get a little bit lower because you have 2 protons instead of 1, but otherwise it's the same idea. But now we put 2 electrons into the bonding orbital, and then we still have 2 more electrons to put in, and so they go into the anti-bonding orbital. If we calculate the bond order, we get 1/2 times 2 electrons in bonding orbitals minus 2 electrons in anti-bonding orbitals, and our bond order is 0. Essentially what we get is that this molecule doesn't exist. There's no net energy holding it together. All the energy gained by putting electrons in the bonding orbitals, so the fact that this is lower leads to stability, is offset by the energy that is lost by putting electrons in anti-bonding orbitals. And so helium dimer, what we would call this He2, does not exist. Or at least it's really, really hard to make. And so under normal conditions, and I can't think of any exceptions to this, helium exists as what we call monatomic gas. It's just Helium hangs out by itself. It doesn't lower its energy at all if it mixes with another helium atom, and so it just hangs out by itself. Okay, so that's our first introduction to molecular orbital theory. So we combine atomic orbitals, and these orbitals now spread over the whole molecule, and we form bonding orbitals, anti-bonding orbitals from the 1s electrons in hydrogen and helium. In the next video, we're going to extend this to our second row of the periodic table, looking at the, again, homonuclear diatomics, the diatomic molecules with two atoms made from the same atoms. So we're just going to go across, starting from lithium all the way over to neon, looking at the molecular orbitals and the patterns that we see here. And along the way, we're going to explain why is N2 diamagnetic, but O2 is paramagnetic.